Hi again. All right, so we've done the ideal gas law, and then I give you another kind of simplistic relationship with it. I want to now um, do a couple of examples of the ideal gas law, and then ask the question, what difference does it make if we change pressure instead of changing temperature, or we change the volume instead of changing the pressure, or we change both the volume and the temperature, holding the pressure fixed, or various combinations of fiddling around with P, V, and T. And for the time being, we're going to leave the number of moles fixed. I don't want to, it's going to be complicated enough without doing that as well. So again, we'll have a closed system. So let me do a few calculations, and then I'll do a thing with them. Okay, so let's see. Let's have an example. Let's do our first example here. And suppose that our system has a pressure. We measure the pressure somehow, and we find that it is about 7.5 times 10 to the third pascals. Assume that we have 1 mole of whatever our ideal gas is. By the way, the assumption that our gas is ideal has a consequence, and that is simply that I don't have to care what kind of a gas it is. Since it behaves in an ideal fashion, it can be anything anything you want. So I was just giving myself some room here. So anyway, let me rewrite this, example 1. Okay, so we'll start out, I'll do this first here. N is equal to 1 mole. So we're going to leave that fixed for all the examples. Okay, so our first pressure, as I say, is about 7,500 pascals. And suppose that we put it inside a container whose volume is 1 cubic meter. It's worth pointing out, it's worth going off camera here. I want to show you something. And that is, how big 1 cubic meter volume is. 1 cubic meter is literally, so this is a meter stick, so you can't even see the whole thing. Okay, so that's 1 meter by 1 meter by 1 meter. If you can imagine that box, that's a pretty big volume. Okay, so 1 meter by 1 meter by 1 meter. So big box. We're going to assume it's a fixed, rigid container, cannot change the volume, at least not yet. And anyway, let's see. Is that what I know? Let's see. Yeah. And so let's, with that information, let's calculate the temperature that this gas has to be at. Okay. Now, how it got to be at this particular pressure is a question that I'm not going to worry about here. Let's just assume somehow we accomplished it. We sat there and squeezed on it or did something to it. Okay. Actually, we'll probably be able to make a good guess. When we calculate the temperature, since this is an ideal gas, the temperature has got to be related to how much pressure there is inside the container and how much volume is inside the container. Because after all, the bigger the volume, the bigger the surface area. The bigger the surface area, the smaller the pressure, because pressure is force divided by surface area. In any case, so how do we get the temperature? We simply write down the ideal gas law, and in this case, solve for the temperature. And so, hey, I'm off camera. Hi, I'm over here. So the temperature then becomes P1 over V1 divided by NR. Okay, and I'll plug in the numbers that I came up with: 7.5 times 10 to the third pascals. Volume is 1 cubic meter. Number of moles, 1 mole. It's particularly important when you're doing ideal gas law calculations to make sure you stick strictly with the SI system. There's way too much temptation to fiddle around with differing units. There's a lot of units around. There's temperature scales, there's the Celsius temperature scale, and there's the absolute temperature scale, and there's the Fahrenheit temperature scale. There's lots and lots of units for volumes, cubic meters, cubic centimeters, milliliters, liters, blah, blah, blah. And even pressure, right? Atmospheres and pascals and kilopascals and pounds per square inch. You've got to stay in the SI system. Otherwise, you're going to get completely messed up. So make sure you are certain that you're in the SI system. If you're not sure, ask me. Okay, so anyway, and so 8.31 times for joules over mole kelvins. And I worked out those numbers, and in round numbers, this works out to be about 900 Kelvin, which, remembering that the freezing point of water is 273 Kelvin, this is over 600 degrees higher than that. So this is a pretty high temperature, right? And so that explains the pretty high pressure. That pressure there is roughly 7 times atmospheric pressure. No, it's not that big. I'm sorry. No, I'm sorry. It's less than atmospheric pressure. Well, anyway, whatever it is. Big box, not much air. One mole of gas, not that much. Okay. In any case, whatever. The point is that given the pressure and the volume and the number of moles, I can figure out what temperature this ideal gas has to be at. Okay. 1 mole is a lot of gas, by the way. Remember, this was only 2/100ths of a mole. So 1 mole of gas is a lot of, well, it's, 50 times this or something? Okay. Anyway. Okay. Give you a second example. Suppose my pressure is 10 times 10 to the third pascals. My volume is still 1 cubic meter. I'm sorry, no, I told a lie. I'm sorry. My volume now is 3 cubic meters. So somehow I managed to make my box bigger. Okay. The temperature has gotten the same way. T2 is P2B2 over NR, which I could pre-calculate NR if I really wanted to. Anyway, and then you do this, and the number turns out to be noticeably higher, 3,600 Kelvin. And then a third example. If P3, this should be P2, I'm sorry, P2, B2, yeah, P3 is 2.5, much lower pressure, 2.5 times 10 to the third Pascal. And V3 is, yeah, I'm reading it off of my page over here. V3 is 2 cubic meters. The corresponding temperature works out to be 600 Kelvin. Okay. So that's all fine and dandy, no real problems there. But now I want to introduce a question, what happened in going from this first state to the second state and then perhaps to the third state? What can I say about those things? Okay, and I offered up the question at the end of the previous recording: does it make a difference how I get from my first state to my third state? Because I described it. There's various ways you can do things. You can change pressures, you can change volumes, you can change temperatures, and changing any of these things is going to affect the other two things. And changing two things at the same time is going to have a big effect on, well, the third thing as well as the two things you're changing. It's all very complicated. So what can we say about it? I'm going to give you kind of I shouldn't say hand-waving argument. I won't do a hand-waving. Let's say, let me give you a qualitative sort of picture description of what's going on. And I'll do it by means of drawing graphs. So let me summarize the values here. Let me move over here first of all. So I'm going to give myself a little space here. And I said, okay, for state 1, my starting state, I'm only going to list the things that are different in the in the 3 states. Okay, the first pressure was 7,500 pascals. The first volume was 1 cubic meter, and the first temperature was 900 Kelvin. State 2, we had 10,000 pascals. V2 was 3 cubic meters, and the corresponding temperature was 3,600 Kelvin. And then 3 was just 2,500 pascals, intermediate volume, and therefore a different temperature, V3 here, just 600 Kelvin. Now, you should spend some cycles convincing yourself that it's reasonable that the temperature here should be significantly lower than the other two. Okay, but let me do this. In each case, what we did was we were given the pressure and volume, and we were asked to then determine the corresponding temperature. So let me display that idea on a graph, or actually a sequence of graphs. And my graphs, first of all, are going to be, reasonably enough, pressure on one axis and volume on the other axis. Okay, and what I'm going to do, in fact, I think I'll do this. I'm going to do this. State 1, I'm going to color that purple. State 2, I will color that blue. And state 3, red. Okay, and so my purple state, let's see, let me put some numbers on here. So I had 1 cubic meter, 2 cubic meter, 3 cubic millimeters, so this is going to be 0. 1, 2, 3, 1, 2, 3 cubic meters. Okay, and on my vertical axis, pressures, I had, what did I have? 7,500, 10,000, 2,500. So let's label this 10. Actually, let me make this a little easier on me here. Let's make this unit kilopascals. Right, that 1,000 pascals, kilopascal. All right. In which case, my first data point here is the volume is 1 cubic millimeter, and my pressure is 7,500. So halfway up, is 5, so that's 5 right there. Out of the way. Okay, so that would be 5. So 7,500 is roughly there, so 1 cubic meter. Okay, so that's state 1, roughly. State 2 in blue is 3 cubic millimeters and 10,000 pascals, or 10 kilopascals, and so we are about there. Okay. And then finally, state 3, we are at just 2,500, which would be down here, and 2. And I'll even label these 3, 1, and 2. Cool. All right. Now, as far as the question about how do we change the system from state 1 to state 2 to state 3, I can display that on the graph, but it's a little bit tricky because I start here and I end up there. How do I do that? Well, I could either change the pressure and then allow the volume to change, just sort of inevitably without thinking about it, just say as I change the pressure, the volume changes. Okay. Or I could say, but that doesn't seem reasonable because if I'm increasing the pressure, I'm going from 1 to 2, I'm increasing the pressure, but the volume is also increasing. That wouldn't happen naturally. Right? If I increase the pressure on something, that can only be caused by decreasing the pressure, perhaps, unless I'm changing the temperature, which of course I am. But I talked about before about squeezing this. I increase the internal pressure by increasing the external pressure on it. So increasing the internal pressure sure doesn't look like it's going to increase the volume. Well, I don't know, maybe it will. On the other hand, if I heat this up, if I increase the temperature, then that's going to increase the pressure, and that in turn will increase the volume. So maybe that is okay. In other words, once again, we've got 2 variables to worry about at a time. On the other hand, I could simply arrange it somehow that I could increase the pressure without allowing the volume to change, and then once I've got the pressure up to where I want it, 10 kilopascals, then say, okay, now I'll just let the volume expand to do whatever it wants. So I could, for example, then go directly from state 1 go directly from state 1 to state 2, letting both the volume and the temperature change while I'm changing the pressure. That's certainly a possible thing I could do to the system. Alternatively, it's at least plausible that I could say, okay, I'm going to allow the pressure to increase from 7,500 to 10,000, but somehow magically prevent the volume from changing while that happens. Okay? And if I do that, and it doesn't matter at this moment, it doesn't matter how I do that, but suppose I do. If I do, then I would say, okay, then I'm going straight up on this graph, and then once I've got the pressure to where I want it, then allow the system to relax to the higher volume. Okay? In which case, my path that I would take, instead of being, sort of a straight line between the purple dot and the blue dot, it would be, first of all, a vertical line and then a horizontal line. Okay? So I could, either one of those would get me from my initial state to my final state, from state 1 to state 2. Similar considerations going from state 2 to state 3. I could go directly, allowing both the pressure and the volume to change simultaneously and together, and then the temperature will fluctuate however it wants, the volume will fluctuate however it wants, the pressure will fluctuate. We'll get to state 3 eventually. Or I could somehow cause the volume to decrease by 1 cubic millimeter. The volume decreases, but the pressure remains at 10 kilopascals, in which case my graph going from 2 to 3 would trace out a horizontal line heading towards the vertical axis. And then once I've got to my desired volume, then allow the pressure to drop, keeping the system somehow, magically again, at the constant volume while that happens. Okay, so there's a lot of possibilities, and all of them can be displayed on this graph. So now let me do some specific examples. If, for example, I went from state 1 to state 2, and I think I can get rid of these labels now. If I decided to go first, allow the pressure to increase but somehow prevent the volume from changing while that happened, and then go keep the pressure constant while allowing the volume to change. How I accomplish this miracle, I don't care right now. Let's just suppose I can do it. Then the way I would indicate all this on the graph is by these two straight lines with arrows indicating the direction that things are happening. Things are changing. Okay? These aren't displacements in space, please understand. These are simply indications of where I'm starting, where I'm ending up, and how I'm getting there. What state I started in, what state I ended up in, and what was the sequence of events that happened while I was going from state 1 to state 2. Okay? We have names for these things. These are great. This next part of the lecture is a vocabulary lesson. Okay? Well, wait a minute. You know what? I'm going to save that for the next recording. Let me do another one. On the other hand, from state 2 to state 3, I could totally. Maybe not that. I could do that, but let's say I do this. I could take this path, and what would happen here? What this path would be telling me is my pressure would start out at 10 kilopascals, and my pressure is going to drop rapidly, and as my pressure drops, my volume is going to decrease also, more slowly than my pressure drops, but whatever. So my pressure is going to drop fast, my volume is going to change kind of slowly, but I'll get there in the end. But both the pressure and the temperature are changing at the same time, and the clever bit here is doing this in such a way that the temperature remains constant over the entire change of state from state 2 to state 3. And so this would be a constant temperature on this little path here. Constant temp. This here is constant pressure. And then this path here is constant volume, as you can see. And if that's all it was, this wouldn't be difficult. Unfortunately, of course, physicists hate you, physics teachers hate you, and so we make it more complicated than this. I'll tell you about that in the next recording.